The divergence of a vector field is the topic of this video. And this quantity appears in so many equations describing physical phenomena in potential fields, for example, fluid and solid mechanics, and so forth. After viewing this video, you'll be able to explain conceptually what a divergence represents. You'll be able to compute the divergence of a vector field if you're given how that vector field varies in space. And importantly, you'll be able to relate the variation of that vector field in space to the divergence on a more conceptual level. So to begin with our description of divergence, let's imagine a point P in 3D space, and let's surround that point by um, a volume of arbitrary shape. So this is our control volume, which is really just a conceptual um, feature used to sort of define our divergence. The control volume is called B. That's the name of our control volume, and has a volume capital V. And the surface of the volume, it's surrounded. B, our volume, is surrounded by a surface, by a 3D surface, which we'll call capital S. And in this 3D space, there is a vector field. And I'll depict that vector field by lines of flow. So here the vector field is flowing into the volume, and then at some other point it's flowing out of the volume. And this vector field varies in 3D space. As well, okay. So there's our vector field varying around our point B, our point P in our volume V. Okay, so you can imagine a quantity I, which is the integral over the surface, times n hat dotted with the velocity field times dA. So let's talk about this integral here. So let's imagine a small area, a patch of area on our surface here. And it has, this is a small patch of area dA. So let's sketch a blow up of that patch. Again, it's an infinitesimal patch of area on the surface. And normal to the surface, which basically represents the orientation of the surface, is a vector, is a unit vector, n hat. So n hat is a unit vector normal to dA. And every part of the surface has a unit normal vector pointing out of it and perpendicular to it. So if you will, you can imagine this sort of odd-shaped surface looking like a porcupine with a bunch of vectors pointing outward of it at each point of its surface, as Greenberg describes. Now, n hat dotted with our vector field v gives the component of our vector field v normal to dA, right? So in this vector field, we have a patch, and at that point of the patch, there's a vector field. Well, there's a vector part of our vector field here, and it might be pointed in some arbitrary orientation. But n hat times that vector field gives, again, the component of v normal to the plane, or parallel to this normal vector. And so again, the dot product is n hat, which has a magnitude of 1, times the length of v times the cosine of the angle between n hat and 1. And the cosine of that angle gives the component of v parallel to n hat. So if I were to sketch that normal component, like this, so I'm going to sketch this normal component at each corner of our patch here, and you can see that it's making a sort of rectangular volume. And so the length of this, or the height of this volume, is Vn times a small increment of time. So with Vn times dt representing the thickness of this volume, n hat dotted with V times the area times dt gives the volume of material carried by velocity v that passes through the surface. And that's, of course, during the time dt. And therefore, n hat dotted with v dA gives the volume passing through dA per increment of time. It's called the volume flux, and it's measured in volume in meters cubed per second. And thus, if we integrate the volume flux at each point on the surface, at each little patch of the surface, again, I is the integral over the surface, S is the surface, S, and we're integrating the volume flux through each point of the surface, and that gives the volume flux of material flowing out of our volume B. Okay, so the way I've depicted this flow field interacting with this hypothetical volume, some of the flow is flowing into the volume, shown by these arrows, and some of it is flowing out. But the integral shown here is the net outflow of the material through volume B. So I guess it's the net volume flux of material flowing out of the volume. So I is positive if more material is flowing out than in. That is, there's a net outward flux if I is greater than 0. If I is less than 0, then there's more material flux into the surface than out. And this gets us to divergence. And divergence is defined at a point. And divergence is a property of our vector field, and it's defined at point P, and it's defined by the limit as B goes to 0 of our integral here. That is the integral over the surface of B of the net outward flow of our flow field divided by the volume of B. And B going to 0 means that the largest lateral dimension goes to 0. So again, B is this arbitrarily shaped volume around P. The divergence is the integral of the volume of this net volume flux through this surface, but as the largest lateral dimension collapses to 0. So it's basically a surface directly surrounding a point, and it's infinitesimal in any lateral dimension. Divergence is again the outward volume flux divided by volume. So in other words, it's the fractional volume flux out of B. Or another interpretation, it's the fractional rate of expansion of the material at a single point. The divergence is the fractional rate of expansion of the volume of the material at a single point. So for example, if we were describing a chemical reaction in which the material is expanding, then that would have a positive divergence at each point of the material. In contrast, if we were describing a chemical reaction in which the volume was decreasing, then that would be described as a negative divergence or negative fractional change in the material volume. So how do we calculate divergence? According to this definition, this is an integral over a surface of an infinitesimal size divided by the volume of this infinitesimal volume. And that's a calculation that's not straightforward to do. So instead, we can calculate divergence as follows. Turns out that the divergence at a point is equal to the partial derivative of the horizontal component of the velocity with respect to x plus the partial derivative of Vy with respect to y plus the partial derivative of Vz with respect to z. And this is how we would do this in, of course, Cartesian geometry or a Cartesian basis. And another way we can describe that is we can define an operator called del, and it's an upside down triangle with a bar denoting it's a vector-like quantity. And it's defined as the partial with respect to x in the I hat direction plus the partial with respect to y in the j hat direction plus the partial with respect to z in the k hat direction. So it's a vector-like operator. So the divergence of V is analogous but not really a dot product between this del operator and V. That is, the divergence dotted with V is equal to d by dx in the I hat plus d by dy in the j hat plus d by dz in the k hat dotted with vx I hat plus vy j hat plus vz k hat. And if we perform this operation on each of these vectors, remember that the dot product between I hat and j hat and k hat are 0. And so if we operate d by dx I hat with each of these vectors, the only vector that remains, the only term that is not 0 is dvx dx, because I hat dot I hat gives 1. Likewise, if we were to operate this part of the del operator on each of these vectors, j hat dot I hat is 0, j hat dot k hat is 0, and the only term left would be the partial of vy with respect to y, and the same reasoning goes for this last term, like that. So again, a relatively simple way of computing divergence of V is del dotted with V. Okay, so now I've given you a definition of what the divergence is in terms of the fractional rate of volume change. I've showed you how to calculate it, but now I'd like to relate why this way of calculating div V is equal to that rate of volume change. again, the divergence is the limit as the lateral dimension of B goes to 0 of the integral over the surface of B of n hat dot V times each infinitesimal surface area of the volume divided by the volume itself. And so the question we're going to address now is, why does divergence as defined by the del dotted with V equal this? So let's go back to the concept of our control volume around our point P and integrating around along this over the whole surface of that control volume. So we're working in Cartesian geometry in this derivation here. And so we have our X, Y, and Z axis. And in this example, our control volume is going to be, it can be any shape. So it's an arbitrary shape. So in this case, we're going to describe our control volume as a quadrilateral. It's rectangular on any side. And okay, so right. And so in this case, point P is in the middle of our control volume at some arbitrary location X, Y, and Z. And our control volume has a width in the X direction of delta X, a width in the Y direction of delta Y, and then a height in the Z direction of delta Z. And again, we have associated with every surface of this control volume, we have a normal vector. So on this surface, the normal vector is pointing in the along the y-axis, and so this n hat is equal to j hat. On this front face, n hat is equal to I hat. It's pointing in the x direction. And on the top face, for example, n hat is pointing up, and that's equal to k hat. Again, these are unit vectors pointing perpendicular to these front three faces. And there'll be unit vectors also on the opposite sides of these faces, and those unit vectors will be pointing in the other direction. So again, we need to integrate over the whole surface n hat dotted with V times the area of each surface. And so let's look at the front face. Let's look at the contribution of this integral of the very front face. So that's the integral over the front face. This front face, by front face I mean this face right here. It's facing sort of diagonally and outward of the computer monitor here. And that's, we're integrating n hat V across that whole rectangular plane here. And so the unit vector again is in the I hat direction. It's equal to I hat. And we have V, which has an X component, a Y component, and a Z component. And dA in this front face, dA is equal to its width times its height. So that's delta, I should say, dx or dy times dz. And I'm going to describe these as dy prime and dz prime because we're going to integrate, because those are going to be our dummy variables of integration, and we're going to integrate over dy from y minus delta y to y plus delta y. So that's integrating over y. So if our point is centered on point y, then we're going over, we're going to the left by half of delta y, and then we're going to integrate across to y plus 1/2 delta y. And we're going to integrate over z from z minus delta z over 2 to, let me write this out a little more neater, a little bit more neatly. Okay, so it's a double integral from z minus 1/2 delta z to z plus delta z divided by 2. Okay, so we're integrating little patches of this front face over a width of delta y and over delta z. And when we do that, again, the only term that matters here is the component of v that's perpendicular to this face. So these terms drop out. So this integral, I'll rewrite this integral, again with the same, integral is over the same interval. I'm just not going to rewrite that to save a little bit of space. And it's Vx at point x plus delta x over 2, right? So this is a half of delta. So this plane is a half of delta x in front of our point, which is located at x, right? And so that's where this Vx is evaluated on this plane, and it's at point y prime and z prime. And again, we're integrating over dy prime dz prime over this interval. And again, we're using these primes simply because we're using the symbol x, y, and z as this single point in the center of this control volume. And so we need a slightly different name of the variables to describe the integration over the, over this direction in y and z on this plane. So we're just using y prime and z prime as that the different variable name to describe that integration. And what that turns out to equal is the mean Vx on the plane times d delta y delta x. Sorry, delta y delta z. And the mean velocity, horizontal velocity, or the v component of Vx on the plane, can be described as Vx, again at x plus delta x over 2, plus some point on the plane, some point of y and z on the plane that equals the mean. So there's the mean value theorem that states that there is some point on the plane, and that point is again x plus delta x divided by 2, and some particular value of y and particular value of z, where Vx is equal to the mean Vx. So we'll write out this integral of this first face as this. Okay, on the back face, and by the back face I mean this face at point x minus delta x over 2, the integral is equal to minus Vx at x plus, or x minus delta x. Yeah, I better write out that integral. On that back face, we have the integral of n hat dotted with v dA on the back face, the surface of the back face, and that's equal to minus I hat, right? Because on this back face, n hat is going in the opposite direction, in the minus I hat direction, again dotted with Vx I hat plus Vy j hat plus Vz k hat. And I better make sure I'm show the infinitesimal area over which we're integrating. Okay, so just moving to the next page. So again, when we evaluate this integral, the only term that doesn't go to 0, well, minus I hat crossed with j hat and k hat equals 0. So the only term that's left is this Vx term, because minus I hat dotted with I hat is just equal to minus 1. And so again, we're left with V minus Vx evaluated this time at x minus delta x over 2. And we're integrating again over y prime. Our dummy variable is y prime and z prime. And then we have dy prime dz prime. And we have this dummy, or a double integral. And that leads to the minus, after we carry out that integral, we get minus the mean velocity on that face, which again is described as the value at the right point on that face, where that's where the velocity is equal to the mean. And we have dy dz, so delta y and delta z. So now going back to our definition of our divergence, again we wanted to take the limit as the largest dimension of our control volume goes to 0. And in this case, let's just look at the integral along the front and back faces. So we're just looking at the front and back faces and that contribution to the divergence. And we have n hat dotted with v dA, and we're dividing by the volume of our control volume. Right, so our control volume again is named B, has a volume of big V. And so we're again, when we compute the divergence, we got to integrate over the whole control volume. But if we just look at the contribution of these first two faces, the front and back faces, we get the limit again as delta y and delta z go to 0 of, I better give myself a bit more room here. It's the limit as delta y and delta z go to 0 of the front face gave me Vx evaluated at x plus delta x, and at the particular point y1, z1, where the velocity was equal to the mean of the front face. And the back face gave me a minus Vx at point x minus delta x divided by 2 at the point y2 and yz, or and z2, where the velocity on the back face equaled the mean on the back face. And those were both multiplied by delta y and delta z, the area of the back face. And the volume of the whole box is delta x, delta y, and delta z. And as we take the limit as, and oh, I'm sorry, we need to take the limit as delta x, delta y, and delta z go to 0. And as delta y and delta z go to 0, then y1 and z1 and y2 and z2 collapse to the point y and z. So that gives the limit as delta x goes to 0 of Vx at point x plus delta x at point y and z. We've collapsed delta x, delta y, and delta z to point y and z minus Vx on the back face, again evaluated at point y and z, all over delta x. Okay, because this delta y and delta z divide out in this top expression. And you might recognize this as a derivative. So we're looking at the value of Vx at point x plus delta x divided by 2 minus Vx at x minus delta x divided by 2. And that's equal to the partial derivative of x with respect to Vx with respect to x. So carrying out the same reasoning to compute the part of the surface integral due to the left and right sides, that's this back left side and this right side, that gives the partial of Vy with respect to y, and then the part of the surface integral due to the top and bottom faces gives the partial of Vz with respect to z. And so again, we have to sum all those parts, and that is why the integral over the whole surface divided by v is equal to the sum of the partial of Vx with respect to x plus the partial of Vy with respect to y plus the partial of Vz with respect to z. Okay, and so this is the definition of the divergence, and this is how in practice we would compute it, and this this way of computing it is specific to the Cartesian coordinate system. If we were working in a different system, we would calculate the divergence using a different manner, but this is how we would do it in the Cartesian system. And so that's From this, I hope you're able to conceptually explain what the divergence represents. Again, it's the fractional rate of volume change. You can compute the divergence based on what we just covered. And as you start looking at vector fields and looking at the equation for the divergence, you'll be able to relate that vector field to the divergence.